consider the next type of scheduling, so which is round robin scheduling. So in order to understand this, let me consider an example. Make you understand, let me consider an example. So consider that there are three people who just want to make use of the same system, and person 1 wants to make use of the system for 5 minutes, whereas person 2 wants to make use of the system for 3 minutes, and person 3 wants to make use of the same system for 9 minutes. So how can these people be allocated the same system? So if at all the person who want to make use of the system for a maximum time, if he is given, so the person who want to use it for lesser time is going to starve, or he need to wait for a longer period of time. So instead of that, so if at all round robin scheduling kind of thing is used, so then each of the people in the fair kind of distribution is to allocate the people with some time slice. So that is, so maybe that the time slice is of 2 minutes. So if at all the person 1 is going to make use of the system, let him use for 2 minutes, and later the same system will be allocated for person 2, and he will be using for the same time slice. So that is for the same period of time. So that is 2 minutes itself. And then person 3 will be using for 3 minutes. So person 1, he requires it for 5 minutes, but he has used for only 2 minutes. So that person 1 will enter into the circular queue and will be waiting. So that after all the three people will be getting the chance to make use of the system for 2 minutes. So again they will be getting chance to make use of the system for another 2 minutes. So the 2 minutes whatever it has been allocated, so it's nothing but the time slice. So here in case of round robin scheduling, we call it as time quantum. Okay, so that is how round robin scheduling works. So if you consider the processes, let us consider these set of processes P1, P2 and P3, and their burst time is 24, 3 and 3. And if we consider that the time slices of 4 milliseconds here. So according to this burst time and the processes, so P1 has the burst time of 24 milliseconds. So we'll consider that all the three processes have arrived at the same time. So at time 0 itself. So P1 will get its chance to execute first, and then P2 and P3. So the processes will be considered in the order of their entry into the ready queue. So P1 will get its chance to execute first. So as I told you that time quantum will be allocated, and P1 will be able to execute only until that time quantum elapses. So the moment after 4 milliseconds, so P1 has to voluntarily give up the CPU, and then P2 will be executing for 4 milliseconds. But since P2 has got the burst time which is lesser than the time quantum, so P2 will be voluntarily giving up the CPU at 3 milliseconds. So that P4 will be P3 will be executing for the during the next time quantum. So if you consider the Gantt chart here, so P1 executes for 4 milliseconds, that is one time quantum. So one time quantum is equal to 4 milliseconds, and P2 will be executing during the next time quantum, which will be allocated for P2, but since its burst time is lesser than the time quantum, it executes up to 3 milliseconds and it will give up the CPU. So that P3 will be executing up to the next time quantum. So since even P3's burst time is lesser than the time quantum, even this will be giving up the CPU at 10 millisecond itself. So that So obviously these two processes have completed, P2 and P3. It's only P1 which will be there in the ready queue for execution. So the next time quantums will be allocated to P1 itself. So the next time quantum will be allocated to P1 up to 4 milliseconds, since there is none other process in the ready queue. So the same P1 will get the chance to execute in the next further quantums. So it will be completing at 30th millisecond. So in case of round robin scheduling, so if at all the time quantum of the process is less than one time quantum, then the process itself will release the CPU voluntarily, and the scheduler will then proceed to pick the next process from the ready queue. So whereas in case of P1, where the burst time of the process is greater than the time quantum, so then the timer will go off. Once the timer will go off, so that is after the elapse of the time quantum 4 millisecond here. So then the process will be interrupted by the operating system, and the context switch will take place. So that is P1 will be preempted, and the CPU will be given to P2 for execution. So the context switch also need to take place. So obviously, which is time consuming in order to do the context switching from one process to another, and the same process will be placed at the tail of the ready queue. So here in case of round robin scheduling, so the ready queue is maintained in the form of a FIFO, which is circular queue, circular FIFO queue. So obviously you need to calculate the waiting time and the turnaround time. So if at all we need to calculate the waiting time for P1. So the waiting time for P1 is, so the P1 gets the chance to execute first, and later P2 and P3, and this is where P1 will get the chance at the finally it gets the chance and it completes up to 30th millisecond, but P1 need to wait until 10th millisecond in order to complete its job. So further it will be getting the chance to execute. So it is 10. So we need to consider the waiting time of P1 as 10. But since it has already got a chance to execute for 4 milliseconds, so we are going to subtract that 4 milliseconds so that we get it as 6. The waiting time of P1 is 6. So whereas P2 will get the chance at the 4th millisecond, and it's going to complete at that time quantum itself. So it is just 4, and obviously for P3 it is 7. So the turnaround time is waiting time plus burst time. So the burst time of P1 is 24 milliseconds, and the waiting time is 6. So it is 6 plus 24. So similarly, you are going to calculate the turnaround time, and you are going to calculate the average waiting time and turnaround time, average turnaround. So now, when we consider the time quantum, so that is while designing the operating system, the time quantum should be designed properly, and this round robin scheduling is preemptive scheduling itself. So if at all the process gets the CPU for execution, and if its CPU burst time is greater than the time quantum, so the process is preempted, and it will be put back to the ready queue. So hence round robin scheduling is preemptive scheduling. So here we need to consider the time quantum in a better way. That is, the time quantum should not be neither too long, or it should not be neither too short also. So suppose that if you consider the process with the execution time as 10 time units, 10 milliseconds, and if at all you design the time quantum to be of 12 milliseconds, so then it will be completing within one time quantum itself, and there is no requirement of any quantum switch. So whereas if at all you design the time quantum to be of 6 milliseconds, so then obviously it cannot complete in one time quantum itself. So at least one time quantum, a time context switch has to be done. And if at all the time quantum is designed to be 1 millisecond, so then obviously it requires 9 context switches at least. And as we know that context switching is quite time consuming also, because it need to save the details of each and every process, and then it has to put the other process for execution. So the time that is required now to perform context switching is also um, time consuming. So hence we need to reduce this context switching time also. So we have to design the time quantum in such a way that it is not too high or too low. So if at all, if the time quantum is too high, so then it is similar to that of FCFS scheduling itself. So the turnaround time also, it depends on the size of the time quantum.